Let's start with a binary operation over a set A such that A is equal to -2, -1, 0, 1, 2, and is defined by A star B equals to A plus AB. So A is the design table for this operation. This operation is defined on set A, and elements of set A or members of set A are -2, -1, 0, 1, 2. So we're going to design table using this operation. So A star B. So our first operation, we're going to use colon against no. So -2 star, -2 star, -2, -2 star, -2. That will give us -2 plus -2, -2 plus -2 times -2 give us +4, and if you give us -2 plus 4 will give us 2. Just -2 operation 1, -1, -2, -2 times -1 give us 2, 0, -2 operation, -2 operation 1, operation 0 rather, -2 plus -2, 0, -2, -2 times 0 is 0, so it's -2, -2 operation 1, -2, -2 times 1 is -2, that's -4. -2 operation 2. -2 times 2 gives us -4, -6. So -1 operation. -1 times -2 will give us +2 equals to 1. -1 operation, -1, plus -1, -1. -1 times -1 will give us +1, plus equal to 0. -1 operation 0, -1 plus -1, 0. Yes, we give us -1. -1 times 0 is plus 0, which is equal to -1. -1 operation 1, -1, minus 1 times 1 is minus 1 minus 2 minus 1 operation 2 minus 1 plus minus 1 2 minus 1 minus 1 times 2 will give us minus 2 minus 3 minus 3 minus 1 plus 2 minus 3 minus 1 operation. Okay, now 0 operation minus 2 0 plus 0 minus 2 plus 0 0 times minus 2 will be 0 is 0 0 operation minus 1 0 plus 0 minus 1 0 plus 0 is 0 0 operation 0 0 plus 0 0 0 0 operation minus 1 0 operation 1 0 plus 0 1 0 0 0 so 0 operation 2 0 operation 2 0 plus 0 2 0 plus 0 is 0 1 operation minus 2 1 1 times minus 2 is minus 2 minus 1 1 operation minus 1 1 plus 1 minus 1 1 1 times minus 1 0 1 operation 0 1 plus 1 0 1 plus 0 plus 1 1 operation 1 1 plus 1 1 plus 1 times 1 so this is 2 and 1 operation 2 1 plus 1 2 1 plus 1 times 2 so 1 plus 2 is 3 2 operation minus 2 2 plus 2 minus 2 2 times minus 2 minus 4 2 minus 4 is minus 2 2 operation minus 1 2 plus 2 minus 1 2 2 times minus 1 minus 2 is 0 2 operation 0 2 plus 2 0 2 plus 0 2 2 operation 1 2 plus 2 1 2 plus 2 times 1 2 4 2 operation 2 2 plus 2 2 2 plus 2 times 2 4 2 plus 4 6 so we have filled the table, or we have designed the table for this operation. Next is to, from the table, get the answers to the questions from B to C. So it says from the table determine whether the operation star over the set A is closed. The foreclosure property, what we discovered is that we have some elements on this table like -6, -3, 3, 6, which are not in the range of the members of the set A. So you can say since some of the resultant elements from the operation of star on set E does not belong to set E. That is -6, -4, -6, -4, -3, -4, 3, 4, and 6 are outside set E. Therefore, the operation star, therefore, the operation star is not closed on set E. So, according to the closure property, if you carry out a binary operation on a set, the result of that binary operation should produce a third element or a third member which belongs to the set A, from which two elements were combined to get the third element or member. So in this case, remember that this binary operation was defined, was carried out on this set. So you can say -2 was combined to -2, -2 was combined to -1. So it was, everything was from, two elements were picked from this set, and the operation was carried out on this rule of combination. Now, when the operation was done, there were results that were gotten. Now, most of these results were not members of the set. Like -6 is not a member of this set. This set is just -2, -1, 0, 1, 2. There's no -6, no -4. There's no 3. There's no -3. There's no 3. There's no 4. There's no 6. So these elements are outside this set. For that reason, the operation star is not closed on set A. So B2. Commutative. So for any operation to be commutative, where A and B are members of the set R, or members of the set E, we're using the set E, members of the set E. So we say that A star B is equal to B star A. So now let's prove that. Let's pick any number here to see if commutativity or commutative property holds. Let's say we are taking -1 is equal to -1 star -2. So -2 star 1, what is it? -2 star -1 is 0. Is equal to -1 star -2 is 1. Is 1. So this is not equal. So this shows that commutative property does not hold. So this tells us that therefore, since -2 star -1 is not equal to -1 star -2, it implies that star is not commutative. Associativity will hold would if for A, B, and C, then as a set A star, B star C, A star, A star, B star C is equal to A star, B star C. So now let's prove if the associative property holds on this. If the binary operation star is associative on the set A. So that let's pick numbers. Let's say let's try -2 star -1 star 2. Would it be associated to -2? So would it be equal to -2 star -1 star 2? Let's see. -2 star -1, what is it? -2 star -1 is 0. 0 star 0 star 2. So now we have 0 star 2. And here we can have -2 star -1 star 2 -1 star 2. That is -1 star 2 -1 star 2 is -3 -0 -2 star 3 -2 star -3. Now what you observe here is that from this result you see that this table does not have -3 because -3 was not part of the set. Set A -2 -1, there's no -3, so the range of set A started from -2 down to 2. So here what do we do? Since we have -3 on the table, we're just going to use the defined operation. Since -2 star -3 is outside the range of A, we are going to use the defined operation instead. So our defined operation is A star B plus A plus AB -2 star -3. So here is -1, B is -3, -2 plus -2 -3. So here's -2. -2 times -3 will give us +6. +6. -2 plus 6 will give us 4. So what do we have here? So -2 operation -2 is equal to 4. So therefore 0 star 2 equal to 4. So what is 0 star 2? 0 star 2, or let's just say, so therefore 0 star 2 itself is what? 0 star 2 is 0. Therefore 0. So we say okay, therefore 0 star 2 equals to -2 star 2. So 0 star 2 is 0 is equal to 4. Now from this associative, if star is associative, that means what you have here should be equal to what you have here. But from what we have seen, what we have here on the left hand side of the equation is not equal, or it's not the same as what we have on the right hand side of the equation. So therefore we say this is not equal. So 0 is not equal. So since -2 star -1 star 2 is not equal to -2 star -1 star 2, it implies that star is not associative. See, from the table, determine the identity element. So select the identity element. identity element will be E. So from what we know about, from what we know from identity property, A star E should give us A, where E is about the set A. Okay, now so to prove this, we get identity element relations. We're going to try some numbers. So let's say, let's try. Let's try to get out. So here, -2 star, -2 star, -2. Maybe give us -2. -2 is E, and E. If E is identity, it should give us E back, which is in this case -2. But let's see what we are going to get. -2 star -2 is 2. So what is the implication? -2 is not an identity. So the identity element. Next one is -2 star -1. Now it's 0. So since we didn't get -2 back, that -1 is also is not identity element. Next is -2 star 0. -2 star 0 is -2. So -2 star 0 will give us -2. So 0 is an identity element because it fulfills the identity property, which is star E operation E to give us E back. So -2 operation 0 is equal to -2. So 0 is an identity. 0 is an identity element. Let's try another operation to see if 0 is indeed identity element. So for that proof, let's carry out operation on 0. So let's say 1 operation 0. 1 operation 0. What is it? 1 operation 0 is 1. So that is 1. Okay. 1 operation 0 is 1. 2 operation 0 is what? It's 2. -1 operation 0 is equal to what? -1. So all of this indicate that 0 is an identity element. So therefore, the identity element is 0. This element is 0. The binary operation star is defined on the set T, EQRS as shown in the table. We determine with reasons whether T is closed with respect to star, whether star is commutative, whether star is associative. The identity element inverse of S. The given N operation P operation R operation S is equal to P. Find P. Closure property. We're going to look at the table to see if the resultant elements from in the table, if any of them is outside this range of elements in set T. What we have here is PQRS, and what we have any element that is not a member of this set. QSPR, SRQP, PQRS, RPSQ. So all of the resultant elements are members of the set T. So we see that star is closed on the set T because all of the resultant elements of the operation, all the resultant elements of the set T under star belongs to or are members of the set C. For commutativity, A star B should be equal to B star A. So let's see if P star, let's say P star is it equal to okay, let's say P star Q is equal to Q star P from the table. So P star Q is S. What is Q star P? Q star P is equal to S. So what do we see? Let's take another, let's also take another operation. So let's say Q star Q. Let's say Q star Q. This is let's say Q star S. This is just S star Q. Okay, so Q star S is P. What about S star Q? S star Q P. So this is since P star Q is same as Q star P, or Q star S is equal to S star Q, it implies that star is commutative. Three says whether star is associative. For associativity, A star B star C should be equal to A star B star C. For A, B, and C members of the set C. Members of the set C. So now we're going to replace this letters with what we have here. So from the table, can we say that P star Q star R is the same as P star Q star R? Let's find out. P star Q, what is it? P star Q is S. So if we carry out the operation on what's inside the bracket first, we're going to have S star R is equal to. So let's carry out the operation inside the bracket first. That means P star Q star R. What is it? Q star R is equal to Q. So let's carry out these operations individually. S star R is equal to S. S equal to S. P star Q. What is it? P star Q is equal to P star Q is equal to S also. So what do we see? What we have here is equal to what we have here. In all cases, one proof is enough, so we don't need to check other, we don't need to combine other elements. So this one is enough. So it says since P star Q star R is equal to P star Q star R, we say it implies that star is commutative. It implies that star is associative. let the identity element be E. Let the identity element be E. So from identity, I say E star E equals to E. So from the table P star P, what is it? P star P is equal to Q. P star P is equal to Q. So P is not an identity element. P is not an identity element. P star Q. P star Q is equal to S. Since we didn't get P, that means Q is not an identity element. Next is P star R. P star R is equal to what? P star R is equal to P. So this is another R is an identity element because from our definition A star E is equal to E. So compare A star E with P star R equals to P. R is E. So we say R is the identity. R is the identity element. If you want to get further proof, it's called that Q operation R is equal to Q. R operation R is equal to R, and S operation R is equal to S. So any element combined to R will always give you the element back. So that shows that R is the identity element. So therefore, the identity element is R. Let the inverse of okay. Let the inverse of S be S. So from inverse property, S operation S inverse to give us what? E, where E is identity. Where E is the identity elements. So which in this case E is R. So in this case E is R. So say from the table, so if you take any two elements here, row column against row, if they give us if we take P and Q, or P and any elements here, and we got E, which is the identity, that means the operation, the element here is the identity, is the inverse of this operation. So let's start. So P operation P. Now in this case we want to get the identity. If we don't get it, that means it's not inverse. P operation P is Q, it's not R. P operation P is Q, so P is not the inverse. P is not the inverse of S. P is not the inverse of S. So, okay. Now we don't need to go that far. So since the question specified that we should get the inverse of S, so we are going to use the S column against the rows. So let's go with S. So S operation P. S operation P, as you see, is R. S operation P is R. Now, is it the identities? R is identity? Yes. So P is the inverse of S. Let's take other proof. Let's say S operation Q gives us P. You can see that S operation Q equals P. So Q is not the inverse S operation R give us what? S. R is not the inverse. R is not the inverse. S operation S. S operation S give us Q. Q is not the inverse. So what's the inverse? The inverse is P, because S operation P give us R, and R is the identity E. From our property, inverse property, say that S operation S inverse should give us what? Identity. Therefore, the inverse of S is what? Is P. B giving N operation P operation R operation S equal to P. What is find N? It's not P. Find N. That's what we're going to look for. Because we don't have N here. N is not an element, so N is standing for an element here. So it's N we're going to look for, not P. So here, since N is what we're looking for, we don't exactly know N operation P operation R operation S and give us P. So first of all, this one we can get this from the table. So we say from the table N operation P operation R operation S is what? R operation S as S, so equal to P. So since N is what we are looking for and we don't know what the value of N is, we're going to take this as a single element. What will combine to S to give us P? This bracket, let's say N operation P equal to E. So E operation what? E operation S is P. What is this A? Let's check. If E operation S, let's come here. What here combines to S to give us P? Let's look at S and P. So that means Q operation S will give us P. So E from the table, E is equal to Q from the table. So what does this imply? Since A is equal to Q, it means I know that E is standing for N operation P. Let's say N operation P is equal to E. So if E is equal to Q, that it means N operation Q is equal to N operation P is what? Equal to P. So N operation P is equal to Q. So now what we think N would be? We'll come back to this P row. See here, what combines to P to give us Q? We check here, P star P to give us Q. So N must be Q. N is equal to Q from the table. Since N is equal to Q from the table, because Q operation P will give us N is equal to P, sorry. N is equal to P because since P operation P will give us what? Q, which is what N operation P is equal to. So hence N is equal to what? Yes, N is equal to P as a final answer. An operation X is defined on the set X equals to A, B, C, D by the following table. So we are going to answer these questions on this table. Is X closed under star? So let's see. These members of set X are A, B, C, D, and members of the resultant elements from this operation A, B, C, D, operation A, B, C, D. The elements here, the members here are all members of set X. None of the elements here is outside the range of set X. Therefore, we say X is closed. Therefore, we say X is closed under star B. This operation star commutative means for commutativity, so A star B is equal to B star E. From the table, let's pick two elements randomly. Let's say B star. Okay, let's say B star C is equal to C star B. Let's say B star C, what is it? D. And C star B, C star B, what is it? D. So this implies that, like I said, only one proof is enough, but if you want to confirm, you can go down, you can pick any other elements, combine them, and see if the commutative property that holds here is consistent. But now this one is enough, so we say since B star C is equal to C star B, therefore star is commutative. C for associativity, A star B star B star C should be equal to E star B star C for all E, B, and C members of the set R. Can be any set R, which, but in this case I'm going to say members of the set X. So from the table, we use this is C star B star E. This is the same thing as C star B star E. So C star D, what is it? It's B star E, and here's C star D star E, D star E, this is C. So let's see, B star E is B, B star E is B, and then C star G, what is it? Is B. So since C star D star E is equal to C star D star E, it follows that star is associative. Then identity so from identity property, you see is operation equal to E from the table E star E equal to what is E. So what do we see? E is the identity. E is identity elements. Well, let's try B star E to see is still the identity element. B star E, what is it giving us? B is C star E, what is it giving us? C G star even identity already shows that E is the identity element. Therefore, the identity element is E.